Okay, so before we were interrupted there, we were just saying that 99% of the time the normal force and the force of gravity would be the same, especially if you're on any sort of flat surface, that'll typically be the case. The other thing that we really want to notice here is that force of punishment and that force of friction, they're not equal. Our object is accelerating, so it's not that part where the net force is zero, the acceleration is zero. Here we do have an acceleration, we do have a net force. We're going to be using that idea that the net force, when we combine them, is equal to our mass times acceleration. And if I look at the forces that are present on my free body diagram, like I said, the normal force and the force of gravity are equal. In the other dimension, the left-right dimension, we'd have that punishment force minus the force of friction. That'll be our net force. That'll be equal to mass times acceleration. So I'm going to be using that equation right there. The punishment force minus the force of friction. That's my sum, my combination of forces equals mass times acceleration. So I'm going to jump to the next slide here. Using that equation there, given in the problem, our force punishment is 782 and our mass 45 kilograms, our acceleration 12.5. I've just plugged those numbers in and we have everything except for the force of friction. So we're almost done with that part A pretty quickly here. Multiply 45 times 12.5. If I subtract 782 from both sides, I got a negative force of friction is negative 219.5. I do want 3 sig figs. So technically, since it's just 5 and there's nothing after that, I would leave it at 219 newtons. We don't round up unless there's something after the 5. That's one of those weird rules that I feel like most people don't really know. So if you'd written 220 with a decimal place, I would be totally fine with that. So our force of friction, 219 newtons, or 220 decimal point newtons. That's part A. Part B was asking us about what is the coefficient of kinetic friction? What's that coefficient of friction? So we know the force of friction. And if you were to look back to your notes that we took several minutes ago, the force of friction is mu times the normal force. So we're looking for that mu. We know the force of friction. What do we know about that normal force, the other part of this equation? Well, on the previous slide, when we were looking at our forces, we had observed and seen that, as in most cases, the normal force equals the force of gravity, that weight. And we had talked previously about the force of gravity. We're talking about Earth here. It's the mass times our acceleration due to gravity. That was something we went over previously. So I can plug in the mass times 9.81, and I can plug in the 219 newtons, just replacing those things with what they're equivalent to. And I've everything in this equation we have except for that coefficient. So we're just about done here too, just a little bit of algebra. If I multiply the 45 times 9.81, I get 441.45. And then we're going to divide both sides of our equation by 441.45. And remember, mu, that coefficient should be between 0 and 1, and it looks like it will be. And it doesn't have any units because it's just a coefficient. So when we get our answer, it'd be that mu is 0.496. And that would be our answer for part B. We just got one part left. We're almost done here, cruising. Part C has been a little while, so what was part C? Just reminding us. You've probably got it on your notes. Mine's like 3 slides ago, though, so I can't see it. Part C was asking how far does she go in 15 seconds if she started at a rest? So if you look at that, we're talking about how far, we're talking about time, we're talking about starting and rest. This may sound like this is a review of stuff from before, because it is. We're just looking at a one-dimensional motion type of situation. So what do we know? And it's always good to identify our knowns. We've got 12.5 meters per second squared. That's an acceleration. What else do we have? We got 15 seconds. And we're talking about starting at a rest. That's our initial velocity is 0. We're looking for how far. Those are the things we really need for this particular problem. If we're just doing one-dimensional motion stuff like we started the year with, we don't need forces, we don't need masses and stuff. We just need our accelerations, times, velocities, etc. So if I look through the equation sheet, now just one-dimensional motion stuff, the first box we went through, we're looking for how far. So delta x, we know time, we know our initial velocity, we know acceleration. The equation that would involve those 4 things would be that their equation. Delta x equals VIT plus 1/2 AT squared. And if I plug in my initial velocity is 0, I plug in the acceleration that we're given, the time we're given, so our initial velocity is 0 times t is just 0, plus 1/2 times 12.5 times 15 squared. We don't even have to do really any algebra sizing on there. So we just plug in that and we get 1,406.25. We need our units and our sig figs, of course. So we get rounded off to 3 sig figs, 1,410 meters now be our answer for part C. So we took it one piece at a time and figured out our answer. And there we go. We're all done.